of logic gates and logic circuits. The logic circuits are broadly divided into two groups: sequential circuit and combinational circuits. The sequential circuits are flip-flops, counter, shift register. There are so many other categories, but as per the focus of basic electronic engineering, we study flip-flops, counters, and shift registers. In combinational circuits, we will study adders, decoders, comparators, and multiplexers. Out of this, in combinational circuit, the main focus is on adder and subtractor only. Now let us see what is a combinational circuit. A combinational circuit is the circuit in which the output of the logic circuit depends on the values of input at that point of instant, that is present state. It does not depends on the order or sequence of applying the inputs. Whereas in sequential circuits, the output of the logic circuit depends on the state of inputs at the present time, as well as the sequence in which the inputs are applied and the previous state of that input. The important topics of comparisons are shown here between sequential and combinational circuits. If we compare from the output dependence point of view, the combinational circuit output only depends on the present states, whereas the sequential circuits, the logic output depends on present state as well as the past states of the inputs and outputs. The combinational circuit not have any memory of the previous states, whereas sequential circuit mostly have the memory of previous state, that is the previous state of the variable. From the clock input point of view, in combinational circuit, clock is mostly not required, whereas sequential circuit works with the external stable clock, and at the edges or various states of the clock, the various operation sequence is taken place. The examples of combinational circuits are adder, subtractor, code converters, and so on. Flip-flop, shift registers, and counters are the examples of sequential circuits. Let us see the combinational circuit in your syllabus. We will see binary adders. Binary adders are of two types: half adder and full adder. Half adders are also called as 2-bit adder, and full adders are called as 3-bit adder. A typical block diagram of half adder, that is 2-bit binary adder, is shown in the figure here. A and B are the two inputs to the half adder, and the outputs are sum output and carry output. The truth table of half adder is shown. When both the inputs are 0, the sum is 0 and carry is also 0. When A input is 0 and B input is 1, the sum of the two is 1 and carry is 0. When A is 1 and B input is 0, then also sum is 1 here and carry 0. Then we will see last combination when both A and B are 1. A and B are added to each other, the sum will be 0 and carry output will be generated to 1. If you see this expression by observing the truth table, we can write the logic expression for the outputs, sum and carry. We have already seen how to write the expression from the truth table. I will recall you. Let us consider the sum column. If you want to write the expression for the sum output, then in this column, for first row and last row, the output sum is 0. So ignore these rows altogether. And then for second and third row output, write the output terms. The first term corresponds to row 2 is A bar B, and for third row it is A B bar. So in writing the terms of output, first we will discard the rows corresponds to output 0 and then write the terms of input which presents the output corresponds to that row. So in this second row, A is 0, so we will take A complement, and B is 1, therefore we will take B. So first term will be A complement B. And in the third row, A is already 1, so we will take the variable as it is. B is 0, therefore we will take B complement. Now try yourself for the carry output. In carry output, first 3 rows are 0 here. And therefore we ignore those rows. Take the last row. Here you will see the input combinations are A equal to 1 and B equal to 1. And therefore, we will take C is equal to A and B. That is equal to carry. If you see this expression for sum, it is nothing but a exclusive OR operation that is denoted as A exclusive OR B. And carry operation is the AND operation of the two variable A and B. Now from this expression, we have to draw the circuit of the half adder. We have already seen how to draw the circuit using expression. So let us use that logic again and draw. Take the two variables A and B here. Connect these two inputs to the input of the exclusive OR gate. So you are getting the output of exclusive OR gate, that is S is equal to A bar B or AB bar, and therefore here you are getting the sum of the two bits. Again take the two inputs A and B and AND it. You are getting the output of AND gate C is equal to A and B, and that is nothing but the carry bit. And therefore, as we have seen the diagram of the half adder, block diagram of half adder, in this block you will have this circuit of exclusive OR gate and AND gate that generates sum and carry output. Now let us see the next adder. Whenever you are adding multiple bits, normally while adding two multi-bit numbers, we require to add 3 bits simultaneously. Input 1, input 2 and carry from the previous column. So in that case, full adder is required. Let us see. The two inputs are A and B. Those are the two single input bits. And C is the third bit. It is connected to a full adder circuit. Full adder circuit generates the output, which is a sum of two inputs, and add the carry input in that sum. And final sum is generated as sum output here. Whereas if any carry is generated in this 3-bit addition, that is denoted by C0 output. Let us see the truth table now. We have three input A, B and C. We call C input as a C in, because in addition normally this is the carry from the previous column. Okay. Or simply consider as a third bit. And two outputs, we have sum as S and C0 as a carry. So there are 8 combinations of A, B, C exist. And the sum is shown here. Let us see the first row. A and B 0 and C bit is 0. Then sum is 0, carry will be 0. When A and B 0, so partial sum is 0. Add this C in that. So you are getting sum equal to 1 and carry equal to 0. Now A is 0 and B is 1. So add it. 0 plus 1 is 1. Sum is 1. And add C in that. So add 0. So you are getting sum equal to 0 and carry equal to 0. Now next row. Add A and B here. So 0 plus 1 is 1. And add now in that 1 the next bit C. And therefore 1 plus 1, 1 0. That is sum equal to 0 and carry will be 1. Now next combination, here A is 1, B is 0 and C is 0. So 1 plus 0 is 1, plus 0 is sum equal to 1 and carry equal to 0. Next combination, A is 1, B is 0 and C is 1. So we will have 1 plus 0 is 0, plus 1 is say 1 0. Means sum is 0 and carry equal to 1. Now next row, A is 1, B is 1. So 1 plus 1 is 1 0. Plus 0 is 1 0 again. So 1 0 means sum is 0 and carry will be 1. Now consider the last where all the inputs are 1. So 1 plus 1 is 1 0. Plus 1 is 1 1. Means the sum is 1 and carry is 1. So that is the truth table of adding 3 bits. Now if you want to write the expression for the outputs, then as usual we will use the common logic, in which we will drop the rows corresponds to 0 present in the output. Let us consider the sum column. We will ignore row number this 1, 4, 6 and 7 corresponds to 0. Now we have to write the mean terms present in the output corresponds to the sum equal to 1 output rows. So here you will see second row. A is 0 means we take A complement, B is 0 means again B complement and C equal to 1. So A complement, B complement and C. That is the first term we have to read. Now go for the next row, third row. Now you write yourself. A is 0 means take a complement of it, that is A complement. B is 1 means as it is B. And C is 0 means C complement. and therefore the term corresponds to this third row is A complement, B, C complement. Then take the fifth row. A is 1, B is 0, and C is 1. So the term corresponds to this S equal to 1 is A, B complement, C complement. Now 6th and 7th row is 0. Go for the last 8th row where sum equal to 1 and ABC inputs are all 1. And therefore, the term corresponds to this sub output is ABC. And therefore, here the term shown ABC. So there are four terms of all three variables present. You can directly implement this expression, but the circuit will be bigger. So first simplify this expression and then implement the logic circuit. From first two terms, take C in common. You will get in bracket A bar B bar or AB. A third and fourth term, take C in bar common. From term number 1 and term number 3, you can get C in common, and in bracket you will get A bar B bar or AB. And from second and fourth term, take C in bar common. You getting A bar B and AB bar. Whereas A bar B bar or AB is exclusive NOR gate, and A bar B and AB bar is the exclusive OR gate. Exclusive NOR can be converted to exclusive OR just by taking a NOT operation of exclusive OR. And therefore, we will have a exclusive OR operation here and we will take a complement of it. That becomes basically a exclusive NOR gate. And this second term remains as it is. So from this term, you will see the bracket terms are both exclusive OR. Take it common. So A exclusive OR B into C in is the first term, and C in bar is multiplied by A exclusive OR B. Now if you see this expression, consider C in as one variable and the bracket as a second variable. So it is exclusive OR operation of C in exclusive OR with A exclusive OR B. So ultimately, when three inputs are exclusive OR, you are getting sum. Now let us see the table of carry. It's shown here. The carry outputs are 1 for row number 4, 6, 7 and 8. So let us write the term present in the product output C0. Consider the fourth row where the C0 output is 1. Input A is 0, B is 1 and C is 1. So write the product term A bar BC. That is the first term here. Now go to sixth row. The inputs are A equal to 1, B equal to 0 and C equal to 1. So therefore, the product term present in the final product output C0 is A B bar C. Similarly, for the next row it is A B C bar. That is the third term. And for the last row it is A B C. Right. Now simplify this expression using Boolean theorems to reduce the implementation of the circuit. Here from first two terms we will take C in common. So in bracket you are getting A bar B or AB bar. That is the exclusive OR operation. And from third and fourth term we will take AB common. So in bracket you are getting C in bar or C in. So ultimately when any variable is odd with itself, that is C in bar or C in equal to 1. So C bar or C in is 1 and therefore we get A bar B C in or A B bar C in or AB. Now we will multiply the last term AB by 1 plus C in. Any term multiplied with any variable or 1 is 1 and therefore 1 plus C in is basically 1. Now distribute this AB on this bracket. So you are getting AB and ABC in. Now from first term and the last term here, we will take BC in common. So in bracket remains A bar and or A. So A bar or A is 1 again. The remaining term can be written as it is AB bar C or AB. Simplify next. So we come to this term already because A bar or A is 1. Now again we will substitute 1 equal to 1 or C in and multiply it with AB. After multiplication by AB we are getting AB or ABC in. Now from second and the last term take AC in common. In bracket remains B bar here and B. So B or B bar. B or B bar is equal to 1. And therefore, final carry output is AB, this one, plus AC in or BC in. So ultimately, it is a product of three variables AB, BC and C in. That is the carry. Now we have sum as well as carry expressions. Sum is A exclusive or B exclusive or C. And therefore, take a exclusive OR gate with three inputs and connect all three inputs to it. Output of this exclusive OR gate, you are getting the sum A exclusive or B exclusive or C. Now, in the carry output, we are 3 AND operation. So connect the inputs to 3 AND gates as shown in the expression. Here, as per the expression, we connect the inputs. First input for first gate is AB. So you are getting A and B at the output. Then for second input, you are applying the input A, C. So output is of this AND gate is AC. And for third gate, we are connecting the input B and C. And therefore, you are getting the output B and C. So three terms are generated here. You will see the expression that is ORing of the three terms. So we can use one OR gate and all the three terms. And we are getting the final expression for the carry. So therefore, we have implemented the full adder for 3-bit addition. The same full bit adder can be implemented using two half adders as shown in the figure. First half adder will be adding the two bits A and B. Sum S1 and carry 1 will be generated. Then the sum will be added to the third bit by the next half adder with C. And the second half adder will add the sum of the first half adder and C in bit. So ultimately you are getting the sum of 3 bits. And carry from the first half adder and carry from the second half adder is all together you are getting the carry output. That is the final carry output for the full adder. So we have implemented here logically using this block diagram the full adder using two half adder. In this block, we will substitute the diagram of half adder and you will get the logic diagram for full adder. The expression for sum and expression for the carry remains the same that we have already derived. Now application of full adder. It is used as basic building block for multi-bit additions. That is 4-bit addition or 8-bit addition or 16-bit addition of the binary number or BCD number. It is used in digital electronic systems where arithmetic and logic operations are required, like digital diaries, microcomputers, or computer systems. They are used as an integral part of arithmetic logic unit of a microcomputer systems. And that's all about the combinational logic circuit as per your syllabus. Let us go to the another type of circuit called sequential circuit. In this sequential circuit, the output of the circuit not only depends on the current state of the logic inputs, but it is also dependent on the previous states of those inputs and also depends on the instance and the sequence in which the inputs are applied. The output of the sequential circuit may also be synchronized with the clock signal. So let us define a clock signal first. Clock signal is basically a logic signal having two states only, logic 0 and logic 1 as shown in the figure. Logic 0 corresponds to 0 volt and logic 1 corresponds to 5 volt. Here, the age changing from 0 to 5 volt is called leading edge. And the age where the output is changing from high to low is called following edge. This leading edge is also called as positive edge and trailing edge is also called as, or falling edge is also called as trailing edge or negative edge. So if you see the clock, we will see that clock is either in low voltage state or it is in high voltage level state. So the low value and high value time is called as level of the signal, and edges where the output changes from 0 to 1 or 1 to 0 is called as edge of the output. When output changes from 0 to 5, it is called as leading edge or positive edge. And when the output clock changes from logic 1 to logic 0, it is called as falling edge or trailing edge or negative edge. Here, time required for one cycle of the clock is called as time period of the clock. And reciprocal of the time period is the clock frequency. Similarly, the high time divided by total time period of the clock is called as duty cycle of the waveform. Now let us see the first building block of a sequential circuit, that is flip-flop. Flip-flops are basically having two stable state. It is also called as a bistable circuit. Here, the implementation of the flip-flop using two NAND gate is shown. Basically, these two NAND gates are connected as inverters, that is NOT gate, and B1 input is connected to first NAND gate and B2 input is connected to second NAND gate, and the outputs are cross coupled. So there is a feedback from output to the input of the next gate. And due to this feedback, the circuit will be going from one stable state to another stable state whenever the input combination changes. That is mentioned here. The state will be changed as per the condition at the input and applied clock, if clock is used. If clock is not used, then the output condition will be only depends on the condition of the inputs. Construction wise, it is similar to a cross coupled inverter. There are various types of flip-flops available in theories. As per the clocking methods, the flip-flop can be level triggered, in which there are positive level triggered flip-flops and negative level triggered flip-flop. Positive level triggered flip-flop changes the state when the logic state of the clock is high. Negative level triggered flip-flops changes the state when the clock is in low state here. The another category of the flip-flop as per the clocking method is edge-triggered flip-flop. That is called as positive edge-triggered flip-flop and negative edge-triggered flip-flop. So in this flip-flop, the change of the flip-flop output will only taken place on edges of the clock, that is this leading edge or on trailing edge. That is called positive edge or negative edge. The another class of flip-flops called latches. That is basically the extension of flip-flop. Latches have again two stable state, that is nothing but it is a bistable state circuit. And latches are used to latch the status of the input when clock is applied. When no clock is applied, it will hold the status of the input indefinitely. So new data can be clocked in latches with the clock, and they can be either positive edge trigger or negative edge triggered, or they can be positive level triggered or negative level triggered. Various flip-flop in various categories are listed here.